Hello students, I welcome you all to this video session of electromagnetic waves module 2 class 2. Myself Dr. Mahantesh K, Associate Professor from Department of Electronics and Communication Engineering, SJBIT, Bangalore. In our previous video, we have understood the concepts of applying Gauss law to the point charge, line charge and a volume charge densities. In this video, we will be applying Gauss law for some symmetrical charge distributions, and also we will try to derive an expression for field due to continuous volume charge distribution. Let us just take up an example. A 50 centimeter length of coaxial cable has an inner radius of 1 millimeter and an outer radius of 4 millimeter. The space between conductors is assumed to be filled with air. Now the total charge on the inner conductor is given as 30 nanocoulomb. We need to find the charge density on each conductor and the expressions for electric field intensity and flux density. Now as per our previous derivation, we have applied Gauss law to a coaxial cable. The relationship between the charge and the charge density of inner cylinder is given by Q. Inner cylinder is equal to 2 pi A, that is radius, L length rho s of inner cylinder. Therefore, rho s is equal to Q by 2 pi AL. Substitute all the given data to this equation. We will be getting rho s is equal to 9.55 microcoulomb per meter square. Likewise, if we calculate the total charge on the outer cylinder, which will be equal to minus of Q in inner cylinder, and we can calculate it as rho s of outer cylinder is equal to minus Q inner cylinder divided by 2 pi BL. Substitute all the data to this equation and you shall get minus 2.39 microcoulomb per meter square. Now, since we have applied Gauss law to a line charge, a point charge and a coaxial cable, now we shall try to apply Gauss law to some symmetrical charge distribution. And we will obtain D is equal to A rho s by rho and E is equal to D rho by epsilon naught. So now I will apply Gauss law to differential volume charge distribution. If we now visualize a region of space filled with a tremendous number of charges separated by minute distances, we are now going to apply the methods of Gauss law to a slightly different type of a problem, a surface without symmetry. We have to choose a very small closed surface that D is almost constant over the surface, and a small change in D may be adequately represented by using the first two terms of the Taylor series expansion for the flux density D. And the result will become more nearly correct as the volume enclosed by the Gaussian surface decreases to 0. So Taylor series expansion we already studied for any given x naught. So the output will be the function of x naught. So for any small variation of x naught plus delta x, the output will be again a function of x plus delta x. A point near x naught is given by f of x is equal to f of x naught plus f dash x naught by 1 factorial into delta x plus f double dash, that is second order differential x naught divided by 2 factorial delta x square and so on till the nth factorial. So we are going to consider only the first two terms of the Taylor series expansion. Only the linear terms are used for the linearization. Therefore, consider any point P located by a rectangular coordinate system. The value of D at any point P may be expressed in rectangular components, that is dx, ax, dy, ay, dz, az. Now we choose our closed surface. It will be a smaller rectangular box centered at P having sides of length delta x, delta y, and delta z, and apply Gauss law. So the Gauss law can be applied in terms of closed surface integral dds is equal to q. So what is dds? dds is nothing but the closed surface. It comprises of 6 different integrals, one with respect to the front and back of the cube, left and right, top and bottom of the cube. Now we shall consider only the front surface in detail, and then later we shall try to apply it to the other sides of the cube. So the surface element is very small, thus d is essentially constant over the surface. It is given by bd front dot ds front. bd front dot dy dz in the direction ax. Why? Because the differential surface is in the direction normal to the ax. So dx front dot dy dz. The front face is at a distance of delta x by 2 from P, and therefore dx front will be equal to dx naught plus delta x by 2 into rate of change of dx with respect to x. So that gives me an equation dx naught plus delta x by 2 dou dx by dou x. We are now for front face, that is integral for front. Integral of front face is equal to dx naught plus delta x by 2 dou dx by dou x with respect to dy and dz. So that is the surface integral. In the same way, the integral over the back surface can be given as, okay, so surface integral of minus dx naught plus delta x by 2 plus dou dx by dou x in the direction dy dz. So if you combine the two integrals, I will get surface integral of front plus back is equal to dou dx or dou x into delta x, delta y, and delta z. Similarly, with respect to the other sides, that is right and left, I would get dou dy by dou y, delta y, delta x, delta z. Similarly, top and bottom, dou dz by dou z, delta z, delta x, and delta y. These results may be collected to yield dds is equal to dou dx over dou x plus dou dy over dou y plus dou dz over dou z of delta x, delta y, delta z. Repeating the same process, so these results may be collected to yield the following equations. The previous equation is an approximation which becomes better as delta V becomes smaller. So charge enclosed in volume delta V can be written as dou dx over dou x plus dou dy over dou y plus dou dz over dou z into delta V, where delta V tends to 0. So now we shall solve a simple problem, application of a Gauss law for differential volume element. Note down this problem and take it as an assignment, so that you'll be trying to find a total electric flux passing through the surface with the given coordinate values, and also find electric field at some point P, and also find the total charge contained in an incremental sphere having a radius of 2 micrometers centered at P 3,2,1. So this would be the solution for sub-question A. And for sub-question B and sub-question C. Thank you for watching this video. I hope you have enjoyed this video on field due to a continuous volume charge distribution for an asymmetric surface with a small volume. Hope you enjoyed this video session, and we shall be joining back on the third video of second module, continuation of volume charge distribution. Thank you for watching this video. Take care. Have a nice day.